All right, test 2, Friday, February 26th at 7. Please arrive about 15 to 10, 10 to 15 minutes prior. And then at 7, or just a few minutes before 7, I will open up the breakout rooms for you to be assigned to. It'll happen automatically, just like last time. Just automatically, you'll go to those rooms and the proctor will be there and you'll have your ID ready. Don't forget to have your ID ready. And then we can take a screenshot of your ID. All right, it's exactly the same as test 1, where you will just open up OWL and the test will be there. And it will run for 2.5 hours, 30 questions. Also next week will be module 9 review. So the final will be based on modules 9, 10, 11, and 12. So test 1 was based on 4 modules. Test 2 is based on 4 modules, and the final will also be on 4 modules. So modules 9, 10, 11, and 12 will be for the final. And you guys, you should have your schedule for the final exam for April. Has anyone seen their schedules yet? It's should be on your student center, right? Final exam schedules are now out. Yes, so you can plan accordingly. I think we are scheduled for April 24th at 9 a.m. Eastern time, right? Okay. All right, so there's a bit of time, and because of that, there's only one assignment left, assignment 5. And because our final is not until April 24th, I'll probably give a nice long extension for you to write that, to complete assignment 5. Okay, because it too, just like assignment 4, it is worth 5% as well. Okay. Also next week, not only the review, but also quiz 9, not this Friday. It's going to be, I believe, let's get this correct. It'll be March 5th. So let's correct these. These are older slides. So will be Friday, March 5th, based on module, not 8. Let's update module 9. Okay, so right, the review for module 9 and then the quiz for module 9. It's just a progress quiz, same as before, 10 questions, right? Okay, any questions on the coverage? Now, I have also uploaded a formula sheet, which you can have handy, have it ready for quick reference. There's also the end of each chapter in the textbook. There are summaries, right? It's some chapter summaries, which are really good for reference. But this should give you an idea of the coverage too. So sampling distributions and the corresponding formulas, right? We have the central limit theorem there. And then one sample confidence intervals, right? Whether sigma is known from previous studies, or this one here, looking at where the standard deviation is calculated from the sample. And then there is also the proportion confidence intervals for the true proportion, and also for the variance. Determining sample size is also covered. One sample hypothesis tests, the test statistics are given here for quick reference. You might have a Z or a T, and you want to really look at the narrative of the question. So take a good look at the sample practice test, and it's through the narrative of the question that tells you whether you should use Z or T. And one way to know if it's Z is if, based on previous studies or somehow you know from the distribution that the standard deviation is sigma, then you use Z. If the standard deviation has been calculated from the random sample that has been obtained from the population, then you use T. S and T are always paired together, and sigma and Z are always paired together. Right? And this one here, this one, I've included this one because it's for a finite population. If it's not a finite population, I'm just going to move my keyboard here. If it's not a finite population, which many cases we don't know, it's just x bar subtract mu divide by sigma over square root n, right? That's the Z formula. When we don't know the size of the population that our random sample has been taken from. Most of the time that this is the case. We don't usually know. Okay. And if it, yeah, with the T, you can see with the T, the test statistic changes, right? If it's T would be x bar subtract mu over S divided by the square root of N. Okay, so that is when you calculate the standard deviation from the sample, which is most of the time. This is the more realistic using T. That's why it's commonly called the T-test, right? Or for finding the probabilities using the sampling distribution for the sample mean. Right, and so there's your one sample hypothesis test right there for ZT for the proportion. For the variance, you use these test statistics. These are all test statistics. We also call these the observed score or the observed T or the observed value, as opposed to the critical value. The critical values come directly from the table, and you should know that by now from working on the previous chapters and also from assignment 4. I should have the grades for assignment 4 posted by tomorrow at the latest. Okay. 2 sample confidence intervals. This again is if the variances or the standard deviations, and you just square them, are known for some reason based on previous studies, you would use this formula. More realistically, and we would use Z. More realistically though, the variances or standard deviations are calculated from the 2 samples, the 2 independent samples from each of those populations, and then we use T. This is the most common right here. Most common for that. Okay, so you want to really look at the wording of the questions, the narrative that's been given. Is it Z or is it T? Okay, based on what's been given. Okay, and then the proportion. Okay, the difference of the proportion is always Z. You don't have to think about whether it's Z or T. It will always be Z. Proportion is always Z. And why is it always a Z procedure? It's because the sampling distribution for P hat is for the proportion, the sample proportion is always normally distributed. Okay, so it's always Z when you're dealing with proportions. So right up here, notice the Z, and hope you can see my cursor, it's the Z, and then here it's Z, always Z with proportion. So if you find yourself using the T with proportions, you're not doing it correctly. You want to use Z. And you can use the table, which I should be able to have. I meant to get the table, the T tables. Let me just see if I can bring this up. I don't want that. Let me see, formulas. That's the F table. There should be a T table. Here we go. Open. So here is the T table. When we have T infinity, right, when the degrees of freedom hits infinity, that is the Z values that you want to use, the critical values from the table. Okay, and you should know that as well from assignment 4. Okay, so just going to go back to the formula sheet, just want to cover it completely. And then finally, chapter 10, this is the most recent, is the 2 sample hypothesis tests. These are the test statistics. So again, Z or T, when you're looking for the difference between the two sample or the two population means. We're making inferences, estimations for the difference between the two population means. Use Z if you've been given the variances, the sigmas, or T if you have read that it has been calculated from the sample. If it is this one here is for when we have two dependent samples and we take the difference of each pair, then we boil it down to one column. We did that last time with the last module where you boil it down to one column and then you just use that one column and it boils down into a one sample problem. So you have D bar, which is the average of the difference, and then the standard deviation of the difference, that's S subscript D, divide by square root N. Okay, so that's when you have dependence. And the other two are if you have independent samples. Two independent samples are for those. The difference between two proportions, again, always Z. Always use Z when you're dealing with proportions. Here is the difference between two population proportions. And then you put the hats on, that denotes the samples from each population. And in the denominator for the test statistic, we pool them together. We just use a p hat or no hat, I guess. It should really be denoted with a different value. That should just have no hat. So yeah. So just remember that this goes into the denominator where you pool the p together. And then test for comparing if two population variances are equal or not, which is the same as the difference. Use this. I spoke about this at the last module review. If you use this formula, you don't have to worry about the method in the text. This will always work, but use the tables that I provided to take the larger value, whether it's S1, right, the variance of the first population or the variance of the second population, take the largest value and divide it by the smallest value and keep the corresponding degrees of freedom in that order as well. And it will always work for you, whether it's a one-sided test or a two-sided test. Right? Any questions? So what I was going to do, I've been having difficulty getting this to show up. I don't know why, but this assignment never wants to show up for me. Let me see if I can grab it again from here. It's been going a little strange. So let me see if I can bring this up again. Open file. There we go. Okay. They seem to be well done. They're almost marked, almost completely marked. So your grades will be available either today or tomorrow at the latest, so that you can use assignment 4 to study from in addition to the video lessons and the practice exams. Okay. For the test, make sure you use the tables that I have provided, right? If you use software or something else, you might get a different number. The tables that I have provided, I have actually produced those from the software package R. So they are accurate. You'll see sometimes, even in the textbook, some of them were, some of the values are not correct. So, and just for consistency, use the tables that I have provided as well. So they have been produced by me using software. So those are the ones you want to use. And I have actually on OWL, if you're looking for them during the test, I've made them available quickly, right? I think it's right here. Right here. So if you go to course outline and review sessions, tables, just for quick reference. Okay, so if you should have all these open for test 2, have them all open and ready or printed if you prefer. And there's the review sessions for test. So review sessions 5 to 8. This is all the coverage for test 2. So it's all right there. And then the tables. Right. So if you have any questions, just pop them into the chat. I was just going to go through some of these. These are all from assignment 4. Let me just make sure there's nothing else to mention here. So if there's going to be no ambiguity about how many decimal places to carry. You want to remember to carry as many as you can though while you're in the process, right? Throughout your calculation, carry as many decimals and then just round to whatever is specified in the test. Round only the final, your final answer. But it should be fine. Yeah, so that should be good. Okay, so we're looking at this. This question is about smartphones. You're going to test to see whether it is, suppose a product testing group that uses a web surfing test reports your type of smartphone has a battery life of 684 minutes, 11.4 hours. So because you use your phone intermittently and for more than just surfing, you expect or maybe suspect that your battery to have a longer life and decide to investigate. So you can then just collect some data, and let's suppose the data in minutes, time in minutes for 6 weekdays has been given. And then you conduct a hypothesis test using a significance level of, instead of our conventional 0.05, we're going to use 0.025. So that significance level, we denote with alpha, 0.025. That's what you want to use. So in symbols, what is the null and alternative hypothesis? We should have, this is what the claim is, minutes versus the alternative hypothesis. Now it needs to be greater than or less than. We think it's greater than because of the keyword. So it's the narrative of the problem, keyword longer. You're suspecting longer. So the null hypothesis is always equal versus the alternative hypothesis contradicts that. It's greater than or less than or does not equals. What is the critical value for the test? Well, the critical value needs to be, so I always use a star to denote the critical value, which is the table value. So that's going to be 0.025 on n in this case. N equals 1, 2, 3, 4, 5, 6. So n equals 6. So the degrees of freedom will be 5. And we can go to the table and find that. So there will be questions on test 2 on how to do this. So see if this is what you got. So you just want to go to 5 degrees of freedom, that row corresponding to 0.025. So your answer will be 2.571. And you can check and see if that's what you got. And that's how you do that. 2.571. All right, and then it says, what is the decision? So how do you make a decision? Right, so this is the process for decision making. Whether you're going to reject and accept. If you reject the null hypothesis, then you can accept that your smartphone has a longer battery life. Or if you cannot reject the null hypothesis, then the web surfing test reports is correct, right? And so what we need to do is we need to calculate the observed value and that would have been done from the data. So hopefully you got an average of those 6 data points. So the 6 observations, those are times in minutes for 6 weekdays, would come to 724 minutes. And then you need to subtract mu naught. Mu naught is the hypothesized value. And for the standard deviation, because I know that it's going into a formula, the way I did it is I carried several digits because I knew it was going into this formula. So you don't want to chop. If you round it to 42, you're going to get a different value. But for this, I'm marking because some people might have rounded to 2 decimal places for the standard deviation. Some might have rounded to 5 or 6. For this, if you look at the question, I'm just really checking to see what is your decision. So even if there's some rounding issues, you won't lose marks because your decision should still be the same, whether you rounded that way or not. It should come out close enough. So I get 2.330 when I calculate all that, right? And remember, S was calculated from the data. So X bar ended up being, if you add those up and divide by 6, you get 724. And then S, I ended up, just for your own calculations, 8,838 divided by 5. I ended up getting 42.0428, something like that. It should be close. So what you want to do is you want to compare the observed value. This is the observed value with the critical value. Okay, and you want to just go, is T greater than T star, but it's not, right? Our observed value is 2.330 and our critical value is this. So it's always good to draw this. The critical value T star would be 2.571, and everything to the right of that, because it's greater than, would be our rejection region. So the part here that I've shaded in would be the rejection region. And 2.33 would be, that would fall maybe somewhere like here, because 0's here, right? It's not in the rejection region. So it is not greater than critical value. Therefore, we cannot reject. We cannot reject the null hypothesis, right? So that means that the company, the web serving test company, their report, you can't reject that claim. Okay, what is the range of the p-value? Now, some students gave the exact p-value, obviously use software, but what is the range you want? There's no way you can get the exact p-value if you are, in fact, using these tables. So we need to look at the p-value. That is by taking the observed value 2.33 and looking along this row for 5 degrees of freedom. Where would 2.33 fall? And you can see that it would fall between these two, which correspond to 0.025 and 0.05. So that is the range. So if you got that, great. So the p-value is between 0.025 and 0.05. And the p-value, you can make a decision here now. The p-value is not less than, right? If it's less than or equal to alpha, right? Less than or equal, it's not, then same conclusion, we cannot reject. So 2 ways to conduct the test. Right? There's 2 ways to conduct the test, and you can see that we get the same conclusion. If you get a different conclusion, then you've done something wrong. You need to go back and look at the look at the formula. So you always check to see if T is greater than T star. If it is, then it's in the rejection region. Or the other way to conduct the test is to check and see if the p-value is less than or equal to alpha. If it's less than or equal to alpha, then you reject. And we cannot reject because it's not, right? Because if the p-value is a number between, just pick any number between 0.025 and 0.05, just any number between those two values is not going to be less than 0.025, because remember up here, our alpha was 0.025. So in order to reject the null hypothesis, the p-value has to be less than the significance level. And what is the decision of the test? I've already said it. So I gave the range, and then I can basically put that answer here. And then in words, provide the conclusion of the test in the context of the question as though you were explaining it to someone who does not know statistics. Basically, what you would tell, I mean, you would not, tell a manager or a team leader that the p-value is not less than or equal to alpha. And that would just all be mumbo jumbo to someone who doesn't know this test. So what you would say is we conducted a formal statistical test, and we concluded that the web surfing test report of the average length of this particular smartphone is 684 minutes, and we conducted a test to confirm that that is most likely true. Right? You would just say that that is what we would accept. There's enough evidence to suggest that that is acceptable. So you would want to use words in terms of the smartphone for that answer. Not in terms of the p-value or anything, just completely in terms of the smartphone. Okay, any questions with that? I think I wrote it here formally for the TAs to mark. The battery life of the smartphone is not longer than reported by web surfing, or another way to say that is the battery life of the smartphone is not different than 684 minutes, or not longer. Okay, so question 2. Any questions before I keep going? Any questions on the processes, how we found the table value, how we found the observed value? This is the test statistic here. Any questions on how to do that? Because this is the coverage for test 2. If there's no questions, I'll keep going. Question 2, right? You compare monthly car insurance rates for 2 sister cities. So who knows what it is, Toronto and London, or Vancouver and Toronto. You collect data and come up with the following. So we have here sample means 105 and 125. So there is a difference between city A and city B just from the point estimates, right? $105 versus $125. And this must be monthly, because I don't know anyone who has a yearly rate for that. So monthly, 105 versus 125, and you decide to test at the 5% level of significance. So there's our alpha. That's alpha. Whether the monthly, it is monthly car insurance rates are different between the 2 cities. Assume that both underlying population distributions are normal. So in symbols, what is the null and alternative hypothesis? Okay, so see what how you did this. I'm going to check my notes. So you could do this, 2 ways to do this. You could go mu1, subtract mu2 equals 0, or you could go mu1 equals mu2, same thing. Those are both the same. Versus the alternative hypothesis, little a for, so for the null hypothesis, we do not. That little o is not, meaning initial, and then the little a is the alternative hypothesis, so that would be mu1 subtract mu2 does not equal 0, or mu1 does not equal mu2, same thing. Either one is accepted. And why did I put does not equal? Keyword right here. Going to highlight it. Different. Right? So are the car insurance rates different between the two? And in order to do this, you really need to know the standard deviation. So 14, size of 14 came from city A, 14 insurance rates, and then 12 different insurance rates. So it's a random sample of different values with those averages and a sample standard deviation 20 and 9. These then must be, this would be X bar 1 and X bar 2. These would be S1 subscript 1 and S subscript 2, and this would be N1 and this would be N2, corresponding to those column A, city A and city B. Should you use the pool or non-pool t-test? So what did you do here? If you go S1, if you take the standard deviation and divide by the second standard deviation, samples, right? I get 20 divided by 9, which is 2.22. And that says, I mean, in order to use the pooled, so the answer is no. In order to use the pooled, you should have S1, S2 should be between or equal. It's not really, sort of a made up rule, actually. Some statisticians won't use it unless it's between 0.5 and 3. I never use the pooled test, t-test. So that's sort of a hint about test 2. You won't see much on the pooled test because I never use it. Why use the pooled t-test when we have software? I always use the non-pooled. That's what I use. The pooled t-test was convenient before when there wasn't computers, or it was just if you want a quick calculation, but quick calculations nowadays can be done with software, and sometimes there's really not a lot of difference. So I usually use the non-pooled t-test. And if you look at another hint about test 2, you'll see here that there's no formula on the formula sheet that I made up for the pooled t-test, right? I just don't use it. So that is, the reason is because you're assuming that when you use the pooled t-test, you're assuming that the population variances are equal, which is in reality not really practical, because to have two independent populations, when would you have equal variance, exactly equal variances? Even if it's between 0.5 and 2, the ratio is between 0.5 and 2, I still wouldn't, because it just seems to make more sense to be more accurate using the non-pooled t-test. Okay, but it's still good for you to be aware. If you are beyond the course, you might see the pooled formulas being used, the pooled t-test being used, and you'll know what it's from and what it is. So what is the observed t-value? So the observed t-value, now, in order to do the observed t, that's going to be the difference. So you need to use the formula where you take 105, subtract 125, divide by this. Now don't forget, some of you forgot to square in the denominator. They need to be the sample variances. You need to square those to be accurate. That's part of the formula, so you want to square those variances. And then in the numerator, negative 20 divided by 5.94318. I'm carrying lots. I want to carry lots because I want to then be accurate up to 3 decimal places. That will be negative 3.365. And that's 3 decimal places. Okay, so that is how we marked your assignments, see if that's what you got. You might have also given negative 3.365 with the absolute bars, which would be 3.365. That's fine too. With absolute bars, just indicate that it's going to be positive. You can look at that because that is what we do. We can look at the absolute value of the observed t-value and then compare it to the critical value. So what is the range of the p-value? If needed, use the conservative method for the degrees of freedom. And we do need that method, right? We do need to use the conservative method. We just take a look at the smallest degrees of freedom. So that would be the smallest sample size is 12. So the degrees of freedom we would use for this test would be 11 because 12 is the smallest sample size and you just do 1 minus that. And we can get the range of the p-value. So we want to look up 3.365 on our table on this row right here. 11 degrees of freedom, that's the conservative method. And we see that the p-value is going to be, so we want to look up the value, the positive value, the absolute 3.365 would fall about 3.365 would be between these two values, which correspond to those. So they correspond to 0.001 and 0.005. Now, because this is a two-sided test, how do we know it's a two-sided test? It's because the alternative hypothesis was does not equals. So for a two-sided test, we need to multiply those values by 2. Okay, so I'm gonna take that information over to the assignment. So the p-value is between, so it's going to be 2 times 0.005. Actually, I'm going to do, so it's less than that. I want to take the smallest one. And 2 times 0.005, right? Which equals, is that what we want to do? 0.001, yeah, 0.002 and 0.00 or 0.01. So you want to multiply those out. Any questions? I hear someone, I just had a question. Sure, yeah. I just want to make sure I'm getting these right. So 0.001, it's going to be between those two. Which is going to end up being just want to check something. So this is correct, and then 2 times 0.005 is going to give you that. So what is your question on the negative 3.365 part C?
So just my question was like, because when I calculated it, like I did the exact same formula as you, but I got negative 2.7 or negative 2.5.
Negative 2.5. That's quite a big difference.
And like even just typing it on my calculator now, like I type in the exact formula that you have here.
Yeah, maybe there could be. Let me just, does anybody else get that? So you're saying negative 2.5?
Let's see here, negative 2.5238.
Okay, let's just check that. So what you want to do is 105. I've got my calculator here. I'm doing it straight up. So 105 subtract 125 equals negative 20. So the numerator is correct. For the denominator, I am taking 20 squared and dividing by 14. And I'm adding 9 squared, divide by 12, and I get 5.9. So for the denominator, I get 5.94318. So if I take 20 and I divide by 5.94318, I get negative 3.365. So I'm wondering if when you're in the denominator, if you are possibly, like I use this many brackets. This is how I put that into the calculator. So I go square root bracket, 20 squared, divide by 4. So make sure you're squaring too. I'm not sure how you're getting the negative 2.5.
Okay.
You might, let me just do it without the squares. So 20 divided by 1.475998, something like that. Yeah, no, it's even different. So I'm not sure if you're losing, possibly losing, you could be losing all that in the denominator. Like you might be losing some of the values from the square root. It could, if you kind of go just one bracket, 20 squared divided by 14, and then close the bracket, the calculator is going to think you're not in the square root anymore. So it's really important to make sure that the calculator has it all in.
Okay.
Yeah, it's good to check though. So what is the decision? What decision do we make? Well, we have alpha up here in orange, 5%. So what you want to do is you go, well, the p-value is, well, you want to just check, is it less than or equal to alpha? And the answer is yes. So then we reject. We reject the null hypothesis in this case. So when we reject, we can conclude that there is a difference in the monthly car insurance rates for the two cities. Right? So that is the decision, the process for the decision. In words, again, provide the conclusion of the test. So you wouldn't want to say again to a manager or a CEO or team leader that the p-value is less than the significance level, the p-value is between 0.002. You wouldn't want to say all that because it's all statistical terms. You would just want to say, we've conducted a formal test between the city A and city B for the monthly car insurance rates of these two different companies or two different cities, right? And you conclude that there is a difference, a statistically significant difference between the two cities. So another way that you can go, there is a difference in monthly car rates between the two sister cities. That way it's in the context of the question talking about car insurance instead of talking about p-values and significance levels and all that. So for question C, I have a question here coming in. For question C, if I leave the answer negative, will I still get a full mark? You should, yes. You will get full mark if you leave it negative. If you give this answer here, that's good. And if you give the positive, you should give the absolute value bars, should, just for completeness. Right, and in words, we've already done that. So that's, and then, oh, well, I've lost my page. So using the appropriate degrees of freedom, what is the largest observed t-value in the table that would change the conclusion of the test? So instead of getting 3.365, right? Instead of getting 3.365, what value in the table, let's suppose we got an observed value of this one. Well, we would still reject because you can multiply that by 2. You would still reject because we need to be less than 0.05, right? So even this one, right? If the observed value is 2.201, let's suppose, then that would mean we are at 0.025 times 2, which would be 5. Remember, it has to be less than or equal. We would still reject at 2.201. So the answer is the smallest observed value that would change the result of this test where we would not reject would be t equals 1.796. Right? Because if the p-value is less than or equal to alpha at 2.201, we would equal alpha. All right? Because 0.025 times 2 times 0.025, right, equals 0.05. We would be equal. We would still reject the null hypothesis. So the smallest value in this case would be t equals 1.796. A little bit tricky, that one. 1.796. Right? Any questions on that? So that would change that tested that value, that observed value in the table would change the result. We would not be able to reject the null hypothesis. All right, question 3. Any questions before I keep going? All right, question 3, we have dependence. Before and after, we can see that we have differences are normally distributed in the population. So we need another column to make those differences. I hope you were able to go through and make a column, a new column, because whenever you have the same people, notice we have 9 clients, it's the same people. Right away, that is an indication that you have dependence. Right? Because it's the same person before and after. They're measured before and they're measured after. Okay. If they're different people, if we had 2 completely different groups of people, then we would have independence and we would use our procedures just like we did here with 2 cities, right? The monthly car insurance for 2 cities. But here we have 9 clients measured before and after, whatever what was happening. So that we have measurements for before and after. You want to make a column right here that shows the difference, and you want to get the difference is equal to, I ended up getting -3. So the point estimate is equal, d bar is equal to -3. And then what is the 95% confidence interval? Well, I ended up finding, let's decompose this. So it would be d bar plus or minus t star times s divided by square root n. So we need to know all those values. We already have d. I'll make sure that's straight there. It's a d bar. We already have d bar. We need s. So s would be little sd there. You can do a little subscript to denote that it's coming from the difference. I calculated this to be 5.6347, and my n is equal to 9, which means my degrees of freedom is equal to 8. And all we're missing is the critical value for the confidence interval. Critical value would be on 8 degrees of freedom. And because it's a 95, so you need to know how to do these 95 confidence levels. So we need to go to the t-table. I think what I'm going to do is, maybe I should get rid of some of this. Clear the connotations. Come back. Hope I'm able to come back to here. Good. Okay, so we have 11 degrees of freedom, or no, 8 degrees of freedom, right? Because there were 9 clients, so it has to be 8. We look at that row and we want to use 0.05. It's two-sided, so it's going to be, we want 0.025 in each of the tails for the two-sided confidence interval, right? We're going to have this 2.5 in each tail, And the confidence interval will be 95%. So we're going to use that value right there, 2.306. Okay, so that's how you find the values for the confidence intervals. It's a good review for that. So this equals -3 plus or minus 2.306. And then we're going to multiply that by 5.6347, divide by the square root of 9 customers, 9 clients. That ends up equaling -3 plus or minus, I get 4.3312. And then to get the min, it wants them, so I have specified here the minimum and the maximum values rounded to 2. That is going to equal -7.33, that's the minimum, to 1.33. I'm just going to make sure that's what I was, yep. That's rounded to 2 decimal places. Notice prior to that, I carried as many digits as possible, especially for the sample standard deviation of the difference. And everyone knows what this box is, right? You can have 1, 2, 3, 4, 5, 6, 7, 8, 9. You can have 9 measurements in there to get the average -3. And that's the confidence interval, the 95% confidence interval for the true difference, right? So this is a confidence interval for, and it's 95% for the difference between, and it's going to be the difference between before and after. And -3. So we have 0 in that confidence, right? We cross 0. Think of a number line. So we have a number line from -7.33, and maybe zeros around here, and then to +1.33, we cross 0. And when we cross 0, then we would conclude that there is no difference between the clients before and after scores. In other words, 0 difference is likely because it's in the range. You can clearly see that 0 is likely because 0 is within the confidence interval range. Right, so we conclude there is no difference. Do you conclude there is a difference? There is no difference. And you would write that more formally, like some of you did. You did a great job in formally writing your conclusions. So it's good. It's good to know what this all means. Why do a task did not know what it means? So there's no difference. So if you were measuring, say, the clients before and after some sort of seminar, or they're giving a rating of the salespeople or a product, the before and after, is there a difference? You would conclude, based on this data for these 9 clients, the 9 clients given, we would say that there is no difference. So that would be really important to a company, right? To see whether there is a difference in whatever is being measured. Okay, question, why use 2.306? 2.306, I'll use a different color here to show. 2.306 is our critical value T star, and it corresponds to, let me draw it up here, our critical value T star corresponds, this is T star here, and there's going to be a negative T star here, because remember it's plus or minus T star, so here's the positive T star, here's the negative T star, it's our critical value, and we want 95% to be in the middle, and we want 5% divided by 2 in the tail, so 2.5 here and 2.5% here. And if you look that up, so you want to look that up like we did on the table, 8 degrees of freedom gives us, right, in the column 0.025 gives us 2.306. Yeah, if you used if you used 1.96, your confidence interval is going to be more narrow, which is good, but Z is not correct because the standard deviation is calculated from the data, right? We calculate the sample standard deviation it's coming right from the data. Plus, another reason too is there's only 9 observations here. It's we call this a small data set. It's very small. There's only 9 clients. Normally there would be 10,000. If you have, if you have 1,000 or even 400 clients, something like that, you could probably get away with using Z because it's going to be a high enough sample to get away with it. But T, especially when it's small like this, you want to always use T. There's only 9 clients here. So think of the difference, 1.96 versus 2.306, right? It means you are, yeah, it's not as accurate. Right? So you want to err on the side of caution and have a wider confidence interval. It's a wider confidence interval, but it is more accurate. So especially for the test and even in practice beyond the course, if you calculate the standard deviation from the data, it's called S. It's the sample standard deviation because it's you're calculating it from the sample. Then automatically use T. Use the values for T corresponding to the degrees of freedom, which is n-1. Much more accurate. It's very standard across many domains. All right. Question 4. What is the critical? Okay, so this one here, I took an exercise straight from the text. Question 4 is about proportions and what is the critical value from the T table. So I didn't want to have a ton of different answers coming in. I wanted everyone to use the T table, which was the last row. If you look here, the very last row corresponds to the values of Z, right? Infinity, because as the degrees of freedom increase and go to infinity, the T distribution converges to the standard normal distribution. So we're going to put in here 2.326 right here. That corresponds to this value, which is 2% divided by 2, right? Because you want to have 1% in each tail, because you want to have 98% confidence. So that's how you get that value. That's the Z value you'll use. Remember at the beginning of the review, I said whenever you're dealing with proportions, always use Z. And I'm just going to plug in these values. So we're going to have, so this is what I got for this. What is the critical value? The critical value is going to be Z star equals 2.326. What is the 98% confidence interval for the difference between the two population proportions? Give the min and max rounded to 4. So it's going to be p hat 1 subtract p hat 2 plus or minus the Z star, right? Z goes in there. You don't have to put a star with it, but just to show that it's going to be that value times the standard error. Now, I always do the standard error, SE, separate. I'm going to give myself a bit more room because it needs room here because I have a lot of values going in. So that's going to be equal to 0.24 times 0.76 divide by 210. These data come straight from the text. So 0.35 times 0.65 divided by that sample was 176. That ends up being 0.04649. So we have everything we need. The p hats end up correspond to 0.24 subtract 0.35 plus or minus, there's our critical value Z star, 2.326, multiplied by, I'll put a bracket here so it keeps it straight, 0.04649. I'll keep that separate. That ends up being negative 0.11 plus or minus 0.10814. And we need a minimum. So that's going to equal negative 0.21814. Remember, these are proportions to negative 10.89186. Something like that. I'll just round, I guess that would round to 9. And I'll just make sure that's what we got. See if that's what you got. Something's off. Hold on. I got too far ahead. So 0.2181 is the first answer. You don't need the 4. 2, negative 0.0019. I don't know what I was doing there, but that's the solution. It's the answer. There's your confidence interval, negative 0.2181 to negative 0.0019. Yes. All right. Any questions? So it does not cross 0. So 0 is unlikely. So do you conclude that age makes a difference in the amount of savings a worker feels is needed to be secure at retirement? Does age make a difference? Age makes a difference in the amount of savings a worker feels is needed to be secure of retirement. Yes, since 0 difference is unlikely. So 0 is not within the confidence interval range, right? It's negative to negative. So we would then conclude that age then makes a difference. All right. And finally, question 5, our last one here. Short, it's pretty quick. So we want to, just going to go back to the last one. So we have here been given, so these tests are pretty quick, a lot quicker to do the variance test. So you just have sigma 1. So there's the variance for population 1. Is it equal to the variance of population 2? The proportions, or not the proportions, the true variances versus, and I'm going to put here does not equals does. So hopefully you did too. The reason is keyword. We're going to use a significance level, right? There's the significance level right there, 1%, to determine whether the population variances for the number of days to sell a home are different. There's the keyword right there, not more than, not less than, but different in London than in Toronto. So this is the average length of time to sell a home in London, Ontario. I think it's even quicker now. 95, yeah, it was this 9 homes in 95 days with, so they're going even faster. They'll continue to go fast, sell faster. So part B is you take F, put the largest value on the numerator, take the smallest value on the denominator. So what am I doing here? I can just sort of put in. So this one here, the sample variance, the first one had, this one here was S2 squared. And this one here was, that's S1. And this one's S2. Those are the variance, sample variance, S1 and S2. And you can see that the largest one is S2. So we put it, 32.6 is largest, put it in the numerator and divide by the smallest one, and we get an observed F. This is the observed F of 1.27, right? And then we can get the critical value. So I'm going to just put a little star. It just keeps the two straight. Without the star, it's the test statistic or the observed value. With the star, then it's the critical value or the table value. I'm going to just put in a subscript here too, so that you know where I found this. It's going to be 0.005, 9 degrees of freedom, and 8 degrees of freedom. Why 9 and 8? Why 0.005? So it's a two-sided test, so we need to go 0.01 divided by 2. So that's going to be 0.005. That's where I got that from. 9 degrees of freedom come first. So because it corresponds to the sample variance of 32.6, 10 homes right here. Right there. That's N2. And the first one had 9 homes, so that's N1. So my numerator is S2 subscript, right? The variance for the second population. So I want to keep that in line and have 9 degrees of freedom first, okay, and then 8. And then you just go to the table. If you go to the table that says 0.005, does anyone want me to actually show this? I can grab the table. I don't mind. I just need to pull up. You just got to bear with me while I try to find the F table. I apologize. I should have had these ready. I should have had the F table. There we go. Open the file. Okay. So we just want to go to the page that says alpha equals 0.005 because it's two-sided. And it's right here. I want this table here because the significance level was 0.01. And so we need to divide by 2 because we want it to be a two-sided test. So we need to go to this page. And we said 9 degrees of freedom first. So that's going to be the numerator, right? The numerator, degrees of freedom, right? Corresponded to the second population. And then cross-tabulate that with 8 degrees of freedom. That's the denominator. That's denominator. And then here we have numerator. Cross those over and we should get 7.34. That's it. So these tests are quick. You don't need to worry about a p-value or anything. You're just going to compare the observed value with the table value and it's done. So that is the value, 7.34. It's what we got. And what is the conclusion of the test? F. So what we can do is we can say F, the observed F, is not greater than the critical value F, right? It's not in the rejection region. If it was greater, then it would be in the rejection region. And so therefore there is no difference. There is no difference because we cannot reject, right? We cannot reject and so there is no difference between, oh, hold on a second. I'm just messing up here. Yeah, there is no difference between the population variances between the two cities. Yeah, it's all done. All right, and there was a bonus as well. Yeah, so we can just say, therefore, we cannot reject the null hypothesis and conclude there is no difference in the population variances between London and Toronto. No difference in terms of the variance in the length of time to sell a home. Bonus question was, you had to really think about this one for a minute because a 95% confidence interval was constructed for the first 5 academic deans. One, it's not a random sample. It's the first 5 academic deans, which means it's a population. It's not a sample. So when you have a population for the very first 5 academic deans, You don't need to construct a confidence interval. It would be the same if we knew the ages of the first 5 prime ministers of Canada. Why do you need a confidence interval? You don't. That it is what it is. Those are the ages. You can just take the average of those first 5 ages. Same thing here. Just take the average of them. You don't need a confidence interval because they represent a population. Now, had the question said we took a random sample of 5 academic deans during the past 30 tenures or whatever, the past 30 years or 50 years, then you would go, okay, that's a confidence interval because it's coming from a pool of several different academic deans. So there's no randomness. It's not a sample. It is what it is. So if it's not a sample, then it's defined as a population, or as a minimum a subpopulation. But it's still a population, even if it's a subpopulation. So the best way to get the bonus is to say something like the confidence interval should not be interpreted because we have a population, not a random sample. All right, does anyone have any questions before we go? I'll be here for a while. Feel free to chat if you like. Otherwise, good luck on the test, and please review the assignment 4 when they get released today or tomorrow. Okay, good luck.